All right, welcome to CS50. This is the end of week 4, and because you all got here a little bit early, we have a little bit of a treat for you. This is perhaps going to be among the most awkward 6 minutes, though, of your life. The following is not a spoof.
Hey, welcome to the party. The 4 of us, along with hosts worldwide, and you are launching Windows 7 Ultimate software. So, you know what? Let's take a minute or so to tell you about how great it is to host a launch party. You can use house party tools to build your guest list, upload your pictures, which is his favorite, right? And you can even get a party pack. Though you're in your own home, you'll be able to participate with others in this exciting event around the world.
In a lot of ways, you're just throwing a party with Windows 7 as an honored guest. Sounds easy, and it is. But we thought you'd probably like to know what to do to get ready and how some hosts want their party to flow.
Yeah. Well, now the 4 of us got to have our parties a little ahead of schedule. You know, try everything out. So we thought we'd be able to tell you some of the tips that help make our parties really fun.
Yeah.
Now, of course, the first thing you want to do is install Windows 7. Right? Yeah, make sure you do that a couple days in advance of the party. Call customer service if you have any questions.
Exactly.
You got to play with Windows 7 before the party.
Second, look at the activities you and your guests can try at your party and choose the ones that seem to you to be the most fun.
There's a video of each activity from one of our parties, and we have tried them all, right?
Yep.
So you can see how the activity runs. And you know what? There's a handy page of notes to print out that tells you what you need ahead of time. I mean, it helps guide you along the party, right? Print these out, because these are called host notes, and they're at the website.
Hey, again, you don't have to do the activities listed under your party theme. You just look at them all and decide which one seems to be the most fun for your guests.
Right.
And some of the host notes, they list bonus activities.
Oh, yeah.
They're great.
Right.
But you may want to try them, but you have to make sure that you have the right devices on hand.
Right. And now, how the party flows is totally up to you. Now, here's a sample agenda, though, that we each more or less followed.
Right. Now, for the first half hour or so at my party, the guests just came in, had a drink and a snack, and mingled like they do at any good party.
Right.
But many of the activities suggest that you have photos from the parties. So we each made a point of shooting 20 or so photos on the digital camera at the start of the party, too.
Oh my gosh. And, well, when everyone was there and settled, I led an overview of some of my favorite Windows 7 features. I showed my guests things from 2 of the Windows 7 orientation videos, and it took like 10 minutes.
Right.
Oh, you know, it was great. It was totally informal. Like, everyone just kind of crowded around the computer in the kitchen.
Hey, we all started with some of the basic Windows 7 features, right?
Yeah. I mean, it's a good way to get things going, right? Whatever your party is, you got 4 separate videos of each of us doing bits and pieces of this kind of thing at our own parties. Now, after my overview, I went straight to an activity.
Oh, you went straight to the activity. Oh, well, I let everybody fool around with Snap for a little while.
Me too, I did the same.
Yeah.
And then we started an activity maybe 30 minutes later.
Well, either way works, right? You figure out what your guests want and maybe just play it by ear. In any event, we each did an activity or 2.
I did 3 activities.
Oh.
Yeah?
Excuse me.
That's great. The activities each have you talk for a minute or so, and then you set something up so your guests can try. So for the rest of the party, you just leave your computer on and running, and then you let folks mess around with it, right? And the guests may have a question for you or something, or you may want to show them some things, but it was all really informal. Oh, and then when you're close to the end of the party,
Wanting everyone to leave.
boy, towards the end, I showed the guests windows.com/help, and it's a great site for people to get more information, and I found it to be a nice wrap-up.
I agree. Help and how-to is a great way to bring it all together.
Yeah.
And it's a great resource for you hosts, too. You can find out pretty much anything you want to know about the features we're using for the activities.
Good point.
Yeah.
That is one way to flow the party, but again, it's all up to us, you. It's what's right for you and your guests.
Yeah, that's exactly right.
You know, the 4 of us learned quite a few things to help make our parties really a lot of fun.
Absolutely. Here's mine. Make the thing you're demonstrating personal to someone at the party. Like the way I made chips files get transferred by Windows Easy Transfer.
Yes.
Or the way I showed my guests web slices by talking about Frank's online auction shop for vintage concert tee.
Or having folks edit photos of themselves to email home.
Yeah,
Right?
I mean, bottom line, guests love it when the activity is about them.
Hey, another thing. I found that it really helped to name the person to be the first with the hands-on activity and have them pick the next person, and so on and so on.
Oh, yeah.
Yeah, yeah. I think you'll see that in a lot of our videos. It really helped get the guests onto the computer.
Okay, on a more serious note. Decide what activities you're going to do at least a day or two in advance, and watch those videos and read the handouts. And some activities have modest setup. You know, they require certain things for you to have at the house.
Right.
Sure. Like you have to have 2 computers to do the web chatting activity.
Right. And any case, none of the setup is too hard. Right? You need to make sure that you're ready to go when your guests arrive, and there are bonus activities in some cases, and you want to go deeper perhaps into it, and you have to have the equipment to do that. Right.
Hey, it helped me to remember that I'm not a salesman at this party. And I'm not supposed to be a total expert either. This is a brand new product, and part of the fun of a launch party is seeing what you already know and what you can figure out. What is just so simple that anyone can do it.
That is one of the great things about ending with help and how-to. It's nice to be able to say throughout the party that you'll wrap it up with a great resource for any unanswered questions later.
Exactly.
Yeah, exactly.
I think the biggest thing is to be totally creative with the party and the activities. Yeah, I mean, this is your party.
Good.
Yeah,
Good.
exactly.
Can you believe that Microsoft put the launch of Windows 7 in our hands? Are they nuts or what?
Well, maybe by letting you be involved.
Ooh, that was harsh. I mean, I don't know. Really, it does make total sense. Windows 7 is all about the computer user, making everyday tasks more simple, working the way we all really want it to, and making new things possible. This really is our launch.
Yeah, you're right. So it ought to be a party. Have fun out there.
Cheers. Cheers.
Have a good one, guys.
Oh my gosh, I'm so hungry. Let's eat.
So I had 6 minutes to come up with some wise-ass comments, and I've got nothing. Like, that is a genuine commercial for the release of a new operating system. And I realize this is CS50, and we do some geeky things in this class. We encourage you to start your P-sets on Fridays. I did it myself. But my God, if you all start having Windows 7 parties, like, that is over the line. So let me counterbalance this by saying 2 things. One is, if you do have a PC and would like to install Windows 7, CS50 does have access to stuff like this for free. So you can actually go to the software page of CS50's website and follow the directions there for downloading Windows in many different flavors. If you guys are Mac users, we also have, or even Linux, we have access to what's called virtual machine technology, VMware Fusion, VMware Workstation. We'll talk perhaps briefly later in the semester about this. But for now, these are just programs that you can download via our website on a Mac, run them, and inside of them can you then run Windows if you would like. So you may be familiar with this idea of dual booting a computer. Boot Camp is one incarnation of this, but that requires that you restart your whole computer to choose between Mac OS and Windows. Well, that's not really necessary these days thanks to virtual machines. You can literally run Windows inside of a window on your Mac. But unfortunately, Apple does not really let the reverse be possible on PCs, albeit with a few exceptions. So let me now counterbalance this ad with one other from one of our own CS50 CA's groups. This is a good commercial. So the cool people will be going to that party. Oh, and another dance too, so there's lots of competition. But I did forget the best part. Let me toggle over. So this morning, I downloaded 22 pages of notes for how to host my own Windows launch party. So you can do this too. We link to it on the course's lecture page. They have, come on, focus, focus. So you can download these things here. What do I do at the party? Introduce. We'll be making the computer uniquely our own by changing the desktop background. And I only downloaded 2 of the like 5 or 6 PDFs. So anyhow, bless their hearts. Microsoft has been very good and generous to the course, but someone over there is, I think, out of control. So, without further ado, we left off on Monday talking about pointers, which are just addresses. And we also talked a bit about GDB. So in reverse order here, GDB, again, is a debugger. This is a tool that allows you to step through your code and, as the name implies, debug your code. Find problems with it a little more easily sometimes than you can by just reasoning through your own code or putting printfs all over the place. And it's been actually wonderful to see on help@cs50.net the past couple of days and on the bulletin board. A bunch of you, even without much encouragement from us, have actually been trying out GDB before reaching out with a question. So let me make that plea formally now. The next time you run up against a bug, before you think you need to resort to office hours, before you think you need to turn to the bulletin board or email, just fire up GDB, run it on your program, as we saw on Monday, GDB space program name, and then a few of the commands that I introduced are probably sufficient for now to start poking around. Set a breakpoint at main, type next, maybe step, and just walk through your program. And there is on the resources page of the course website a PDF. It's more detailed than you'll want probably in this first week of using GDB, but it's essentially a cheat sheet for all of the things you can do, and you'll probably see me and the TFs do even more than that. So do start there with GDB, and you'll be surprised how powerful it is. So I spent yesterday using my PHP and MySQL skills to whip up a little grades interface for the TFs to input all grades into the course's website, and then for you guys on an encrypted page to view them. So the TFs are in the process of uploading scores you've probably received via email already, but do take a look at the new grades link on the course's website. And this is meant to be a sanity check for you guys, too, to make sure our records reflect what you think you, in fact, received on some PSET or quiz. No new handouts today. OK, so we left off talking about pointers in memory, and we said that this is going to allow us to do a lot more because it's really giving us pretty low-level control of the computer in terms of memory and ultimately hardware, but we also promise that we can do some damage. And we'll see over time how bad things can happen. And frankly, a number of you have already experienced this most recent week, bad things happening, like weird things appearing in your Game of 15 board all of a sudden. And very often we've seen this is the result of your overstepping the bounds of some array, for instance, your board array. So just to quickly recap over here, if you declare something like int x, a little something like that, and hopefully you all can see this, but I'll recite anything I write. So if I just declare int x, pictorially we've been drawing this as a little square. This square is how big in size? 32 bits, aka 4 bytes, and this would be called x, so it has some little label, and it's, in fact, 4 bytes. If I instead do something like this, char c, what does that look like in memory? It, too, is a chunk of memory, but how big is it? So it's just 8 bits, or 1 byte in memory. So this would be C. So the quick recap is chars are 8 bits, or 1 byte. Shorts are 16 bits, or 2 bytes. Ints are 4 bytes. Longs are 4 bytes on these computers these days. And long is, so 8 bytes, or 64 bits. And we have floats and doubles, which are similarly 32 and 64 bits in size. But then we started doing other things. We started saying things like int, let's say, ARR bracket 4. So this declares an array. And so an array in memory looks instead a little bigger. So this is going to look a little something like this. It's going to have a label of ARR. And then what's going to be inside of this chunk of memory when I write this line of code here? Ones. So garbage values, right? We don't know, right? We don't know, and we've seen examples already. If we just declare a variable or declare an array of ints or any data type, who knows what's going to be in there? So again, the one lesson on Monday was make sure to always initialize your data. Otherwise, unexpected things can happen. Now, ARR here is the name of this array. But now you can start thinking of this ARR, the name of this variable, if it's an array, as not just a label or name, but it's kind of the address in memory. Because one of the other things we said on Monday is that when you allocate a whole whole bunch of things in memory by way of an array, they're contiguous. And this is important. Contiguous is in the first int is here, the second int is here, the third and the fourth. They're all back to back in memory. And that means that you can then index into them using this square bracket notation, because the computer knows that the 0th element is right at the beginning. The 1 element is then 4 bytes over. The 2 element is 8 bytes over, and so forth. So arrays give us what's called random access, because you can jump anywhere in the array you want, so long as you know the left-hand side and the right-hand side, or the length. But we'll see in just a couple of weeks that there are other data structures that are actually more sophisticated, but for which we're going to have to give up that feature. Now, what does it take to remember where an array is in memory? Well, yes, you could certainly remember the address of this 32 bits, this 32 bits, this, and this. But again, it suffices, so far as we've seen, to just remember the first address, so long as you also remember what? So the length of the array. So unlike Java, those of you who have programmed before, unlike Java, C arrays do not let you ask the question, how big is this array? At least usually. There are a couple of exceptions. But you can't ask that, so you have to keep it around in your own variable, like n. So we also talked increasingly about this thing. So we said, let's just rotate this around. We started talking more about strings. And a string is just a synonym for what data type? Yeah, so char star, or really a string we've said is an array of characters, but char star implies that it's actually a pointer or an address. So these things too are now kind of the same. If I do something like, if I declare a string, let's actually leave room this time. If I actually declare a string and store in it a short word like foo, I might do string s gets quote unquote foo. All right, and in memory, what does this look like? Well, how many bytes do I need to draw on the board? OK, good. All right, so that was good. Not easy to trip up just yet. So we need 4 bytes because we need F, O, O, and then the \0. And in order to write a \0, the character that's going here, this is the character F. And remember, with chars, you use single quotes. This is the character, or char O, the character, or char O. And then this is also single quote \0 single quotes. So that's all that means there. You may see some textbooks just write a literal 0, but I would say many or most people just use this notation to be clear that this is in fact a char. It just happens to be the actual number 0. But this is clearly the same thing as this. So char star s equals bar actually does the exact same thing in memory, because string and char star are just synonymous, as we'll see in the CS50 library today. So now we have bar \0. So what is s? Well, it's the label, yes, of these actual strings. Rather, it's the label for these actual strings. But it's also, as we're starting to see now, an address. And an address is something that's numeric, and it's something that we're going to be able to perform various arithmetic tricks on to actually really start to manipulating our memory. So with that said, let's take a look at this example here. So this is, again, from the other day's handouts. Pointers1.c. And what I did today was I ran a little script on my own code that removed all of the comments just for the sake of discussion. But your printouts have the actual answers to some of these provocative questions. This program here is pointer1.c. And the first interesting line of code has me calling getString. So this is going to return what? So getString prompts the user for a string. When I finally type some characters and hit enter, what is it that's being returned technically? So conceptually, I'm getting back a string. A little more concretely, I'm getting back an array of characters. But again, return values in a C function can only be one thing. And you can't just hand me a whole bunch of characters. So what am I literally being handed as a return value for getString? A pointer, so an address of that string. So apparently, and we'll see this when we peel back this layer today, getString is actually allocating a chunk of memory. It's saying to Linux, I need a bunch of bytes of memory. I need 4 bytes. I need 8 bytes, whatever. Tell me what address I can start writing these characters into RAM. Because then, once I'm done writing the characters that the user has typed in, I'm going to return to the caller, the function who called me, the address of the first byte that you, the operating system, handed me. All right, so why am I checking for null here? Under what circumstances do you think something like getString might return this special sentinel value null? Sorry? I didn't enter anything, so maybe I hit, for instance, Control D. As you'll see, is sort of an esoteric trick. If you essentially want to tell the computer you're not providing anything, you can send what's called the end of file or EOF signal or character, and that's usually done by hitting Control D. So we need to be able to handle that. But under what other sort of more familiar circumstances might getString not be able to return to me the address of some string in memory? Like, again, start thinking corner cases. What could go wrong? What could a really obnoxious user try doing just to mess with me? Got to be a little more committal. Like, what could go wrong? OK, so just pressing Enter. So hopefully I handle really short strings. And in fact, this code does. What's the opposite of that, right? Again, corner cases generally mean, if you're expecting a number, give it a word. If you're expecting a positive number, give it a negative. See what happens. So in this case, it's expecting a string. Don't give it a string. Or what's the opposite of that? Give it the biggest freaking string that you can just by, holding down your keyboard for a while and then hitting Enter just to see if you can overflow the memory in the computer. Because this too would be bad. Because if the operating system doesn't have a billion bytes to give you, I really went to town on the keyboard and tried typing in a billion characters. Well, if there's not that much RAM in the computer, getString, maybe it could return part of the string, just the first several thousand characters, or something bad's going to happen because it's going to start overwriting important memory, but that's where we would need to check the documentation. And as you'll see in CS50.h, our own header file, which you do have a printout of as well, this is where, in the absence of a man page, can you actually turn for documentation for functions. So if you've got some source code that you're using from us or from something you've downloaded for future projects, I mean, honestly, looking at the source code is a very good place to start, assuming that person has exercised some good design and style and actually documented it. So I'm curious. Let me scroll down. OK, get char. I'm not quite interested in that yet. Get float, get int. And now notice this is a header file. So what do you see and what do you not see in this file? Sorry? So these are all called what here? These things that are not comments. So these are the function declarations or the prototypes. The functions are not yet implemented or defined. So declaring a function means telling me what it's going to look like. Defining or implementing a function is actually writing the code between the curly braces that implements that function. So a header file generally, as we'll start to see today, and you guys have been using sharp including header files for some time, is generally not much code, but rather a bunch of comments describing what this library or what this file can do, and also declarations for things you, the programmer, might need. So for instance, when you've been using standard lib.h or math.h or any of the other .h files that you might have found useful over the past couple of weeks, what you're doing is telling GCC to go look on the local file system, the local Linux hard drive, find the file called math.h, because in that file is a list, just like this, of all of the special math functions someone else put a lot of work into writing for my benefit. And this way now does GCC know what functions I can call. But there's generally one other step. Simply including the .h file with sharp include is only telling GCC that this function exists. How do you then tell GCC where to get the actual bytes that comprise this file? How do you link them in, so to speak? And that's the keyword, link. At what point do you link in the math library? Yeah, so at compile time with the -lm flag. So it's essentially a two-part process. This is sort of full disclosure. Hey, GCC, here comes some functions that I want to use. Here comes some constants. Here comes some synonyms that I want to use. But to actually tell GCC to compile in the zeros and ones that implement this stuff, that live in a different file altogether, probably a CS50.o file or a math.o file, you need that linker flag at the command line, the -lm, -lcs50, and so forth. So we were looking for the getString. Here it is. So apparently getString returns a string. And here's its documentation. Reads a line of text from standard input and returns it as a string sans new line character. So in other words, even though I might type foo and hit enter, apparently this function is going to get rid of the new line character for me and just return FOO and then the terminating character \0. Ergo, if the user inputs only enter, it returns quote unquote, in answer to your question, not null. So there's apparently a distinction here. Null is this special thing which signifies I've got nothing for you. But quote unquote in computer science is generally known as the empty string, which is a string, but there's just no actual readable characters there. So there's a difference. Null is nothing, whereas the empty string represented in code like this is actually represented how in memory, with how many bytes? So there is, in fact, one byte being used to represent the so-called empty string, and that byte simply contains \0. So that's the difference. Whereas null, this special constant null, this is like there is nothing actually there. I'm returning just this special sentinel value. OK, so what about string? Well, all this time we've been saying that string is just a synonym for char star, and this is why. So here at top left, at the top of CS50.h, there's this feature called typedef, where you can define your own data types. And we'll also do this for more sophisticated purposes. But what typedef here is saying from left to right is declare a type called string that is identical to char star. So it's just a synonym. And we only do it at the start of the semester just to kind of simplify things a little bit. But realize, too, you may see things like this. So you don't need to have the star, FYI, right next to the variable name. You'll often see code like this. It generally tends to be clearer, though, if any time you define a pointer moving forward, it is right next to the variable, or in this case, the data type name. So just FYI on that. OK, so now let's take a look again at this code that opened this line of discussion. So here we go with the code. I call getString. I store it in S. I then do a sanity check. If it equals null, just return 1. Bad stuff's going to happen if I try using this thing otherwise. And then this for loop has what? So int I gets 0, n gets sterling, s. OK, so that's sort of boring for loop stuff. But there is something interesting here. What is going on here exactly? So what is s in technical terms? What is s? So it's a pointer, which is an address, which is just a number, right? So every time I draw RAM on the blackboard, I just draw it as a rectangle. And then I say byte 0 is here, then there's byte 1, then byte 2, then dot, 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 byte 2 billion if you've got 2 gigabytes of RAM. So memory can just be addressed numerically. I don't know if it's bottom up or top down. It really depends on how the machine is viewing its chips of RAM. But in this case, we just care that s is a pointer or an address or a number, all the same here. And so what am I doing on each iteration? Well, s is the starting point of whatever string the user has typed in. So if the user has typed in FOO\s, first of all, what is the value of n going to be within this loop? What's the value of n going to be once called here with string length? So it is going to be 3. So when we ask about the length of a string, we mean in human terms, not special computer encoding terms. So the string length here is, in fact, 3. It is not 4, just to be clear. So what is the length of this string? So 0, right? Because there's no actual alphabetic characters or otherwise there. OK, so what is s? Well, s is a pointer. So pointers, we know, are 32-bit chunks of memory, right? So an address, a pointer, is 32 bits. So it looks like an int, but it's a special data type called a pointer. And now what is inside of s? Well, s is technically going to have the address of the first character in this string. So we're going to push the limits of my handwriting ability on a tablet here. But if this is 0x10, this is 0x1. 1, so now we're dealing with chars today and not ints. So a char is 1 byte, so the size of the data type is now important. This is 0x12 and then 0x13. What is actually stored in this 32-bit chunk of memory called s? 0x10, right? 0x10, the address of the first character. Or pictorially, and it's a lot more user-friendly just to start drawing things with arrows, what we essentially have is a pointer pointing to the first character there. OK, so with that said, s is then the address of this first piece of memory. So this loop iterates from 0 on up to 3. So it's going to execute for I equals 0, 1, and 2 on up to 3, but less than 3. So what am I printing? I'm printing a character in a new line on each iteration. And what am I doing? I'm printing some math. So s plus I. So s plus 0 is what on the first iteration? What number? 0x10, right? The hexadecimal value 10, which is just a number represented in hex. OK, so star and then an address tells me to do what? Go there, right? That's all we said on Monday. When you put a star in front of a variable, if that variable is a pointer, or in this case, if you put a star in front of an arithmetic expression that itself is the result of doing math on a pointer, the star just means dereference this, go there. So that means go to this character, and what gets printed? Perhaps needless to say, f. Now we iterate onto the loop again. So I gets plus plus, so now I is 1. So s plus 1 is now OX11, so what gets printed? Right, so now we do a little bit of math. So OX11, go there, so O gets printed. Plus plus, OX12, go there, print that. And then I is now going to equal n, so the loop terminates. Right, so that's all that's going on here. This is what's generally known as pointer arithmetic. And as the name implies, it just has to do with doing arithmetic on pointers. But GCC, or the compiler, figures out whether you want to add 1 byte or 4 bytes, or, as we'll see, it depends on the context. But for now, it's pretty straightforward. Incidentally, why did I initialize a second variable here called n instead of just putting string length here by doing this string? It's never going to work on this. So why did I do the approach I did and not just move it to the condition part? Right, otherwise I'd be calculating the length of the string s every time, and odds are the length of the string is not going to change if I'm not doing anything destructively to the string. I'm just letting it be. So the length is never going to change. Putting it into the condition would actually be fairly stupid, because then this loop is going to have an increased running time just because I'm foolishly checking the length of it again and again and again. OK, finally there's this, and this is new today. What does this probably mean? Free s. Why is that necessary? So there is a keyword heap that we'll get to today. So all this time getString and so all this time getString is actually pretty poorly implemented, sort of objectively speaking. So the CS50 library is all about making it easier to get user input. To do this, we need to allocate memory on demand, but we don't know how much memory you're going to need at first, because we don't know how many words or how many characters a user is going to type in. So we allocate memory, as we'll see today, dynamically. We allocate enough, as much as we need to fit your string, unless we completely exhaust the RAM's capacity, and then we return you a pointer to it. But the problem in a language like C and C++ is that if we hand you memory and you never hand it back, we will assume you're continuing to use it. So fast forward to reality. If you've ever been using your computer, Mac, PC, whatever, for a long time, many hours or even many days before, without even shutting it down, I mean, what you've probably experienced that the machine starts to slow down over time, or hitting Alt-Tab or trying to change windows might start to feel like things are grinding to a halt. I mean, there can be any number of explanations for that problematic behavior, but one of them is that your computer is running out of memory. So not physically, but your computer is running this program and that program and this program, and humans are fallible and probably wrote some buggy code that asked the operating system for memory but never gave it back. In fact, in the worst case, you can imagine a simple application like an instant messenger. Right? Every time you get an IM, whether you're using AOL or MSN or Gtalk or whatever, a string appears on your screen. Well, that string has to be stored in memory somewhere. So even if we just kind of think through intuitively how an instant messaging client works, odds are that memory is being allocated dynamically. Every time you get an IM, maybe, the OS is being asked, oh, someone just sent me LOL. I need another 4 bytes for this. Or a longer sentence. I need an even bigger chunk of memory for this. But if that client never says to the operating system, the user closed the window, here's all of that RAM back, AOL Instant Messenger or whatnot is just going to keep asking for more and more and more bytes. And if you then look at your activity monitor on a Mac or process manager on a PC, you might see that one stupid little program is using many, many, many megabytes, if not gigabytes of RAM, just because the programmer screwed up. And this is how easy it is to screw up. And in fact, any program you all have written thus far allocating memory has been buggy, at least objectively speaking, because probably none of you have ever freed the memory you asked for by way of getString. But today, that all ends. So it turns out that getString uses a function called malloc for memory allocation, and we'll see that today. Free is essentially the opposite. you hand to free a pointer that has been known, that you know points to a chunk of memory that has been allocated for you. So let me go ahead and open now a second variant of this, just to show something a little more sophisticated. And actually, let me clean up one of the conditions for a moment, just to show something slightly different. So this 5 here is kind of a magic number right now, but I just wanted to simplify the code for the sake of discussion. And actually, I'm going to go ahead and delete these 2 lines of code just for discussion's sake. So 3 lines of interesting code now. The first allocates an array statically, as we'll say. If it's static in the sense that I give it the values in advance, and I'm not letting the user provide them, for instance. This is, again, how you statically initialize an array. You can use curly braces like this, and then just put your numbers or your strings or whatever inside, separated by commas. But the loop is essentially the same. Here's a star, and here is some pointer arithmetic. But notice the difference here, and this is kind of neat. So this time the array is not of type char. It's not a string, but rather it's of type int. So an int, we said a moment ago, is 32 bits, or 4 bytes. And yet, when I iterate over this program's array, printing out each of its numbers. So actually, let's do that sanity check. So make pointers 2. Let me run pointers 2. That's all it does. It prints 1 to 5. But notice how I'm doing that. I'm iterating from 0 on up to 5. But each time, I'm doing the exact same arithmetic. So I'm taking numbers plus 0, numbers plus 1, numbers plus 2. But that feels kind of buggy, right? If an int takes up 4 bytes of memory that looks kind of like this, and I print the first int, well, that makes sense. The 32 bits representing the number, say the number 1, gets printed. And so the width of this thing now is 32 bits from left to right. So this here is my pointer called numbers, and it's pointing to the start of this element, and I print out those 32 bits. But if I then add 1 to it, that sort of means that this arrow is not pointing there, but it's kind of pointing here, right? Because that would be 1, this would be byte 2, and this would be byte 3. And then we'd have the next byte of starting at another 4. So is this buggy or not? Actually, this is kind of a leading question because you wouldn't know the answer. So no, it's not buggy, because one of the features of this thing called pointer arithmetic, and this is just really to hammer this home so you don't yourself do the wrong math, GCC is smart enough to realize, oh, this pointer here is a pointer to an int. I know from the way I was designed that an int is 32 bits, or 4 bytes. Therefore, any time someone tries to perform arithmetic on me, like with plus 0, plus 1, I'm really going to do plus 1 times the size of me, plus 2 times the size of me. So what this means is numbers plus I times 4 is really the mathematics that are going on. And that's what lets me go from left to right across the array correctly. And I'll leave that updated version of the code there. OK, so any questions before we start peeling back the layers of a library here? No? OK, so here is a use of the CS50 library. It says printf, say something. This is an example that uses the library. Printf, say something. Char star s1 get string. So really starting today and starting with pset 4 onward, like no more string. It's char star. That particular training wheel will come off. Allocate enough memory for copy. OK, interesting. So the context here is that I wanted to write a little program that lets me copy one string to another and then actually demonstrate that the copy is correct. So this is excerpted from this code here. This is copy1.c. And it's not terribly long, but it uses the same building blocks. So up here, I say something. All right, that's not that interesting. Here I say get string, and then I do a sanity check. OK, so at this point, and as your printout suggests, I can comment those 4 lines of code with one comment, like get input from user or whatever. All right, so now this is a little worrisome here. What in English is this line of code doing? What is it copying? So it's just copying the memory address, and it's taking the value in S1, which is an address, a pointer, and it's storing it in S2. So at this point in the story, S2 is a copy of S1. But conceptually, S2 is not a copy of the string pointed at by S1. In fact, let's take a quick look. So I'm going to make copy 1. I'm going to then run copy 1. And I'm going to say something like, hello there. it didn't seem to capitalize the whole thing. Let's try this again with another word in all lowercase. Foo, lots of lowercase letters. Oh, OK, no, that's correct. I had to think about it. But what's wrong here? This is buggy. So the goal is to capitalize the original, or to make a, oh, actually, I should tell you what the point is. The goal of this program is to take the original string, make a copy of it, and capitalize the copy. But clearly what's happened here is both have been capitalized. So let's take a quick look at the code and then see what it actually takes to fix this, not for the sake of fixing it, but for the sake of understanding what's going on underneath the hood. So at this point in the story, we have a string called foo or whatever in memory, and I'll keep it short so that my handwriting doesn't completely fail us. So I have a string called FOO\0. I have a pointer called S1, and that is effectively pointing to this byte in memory the moment getString returns. OK, it is not null, so I don't return yet. I proceed to the next line. This line of code here, where it says S2, similarly declares a pointer of size 32 bits. Even though it's pointing to a char, the pointer is still 32 bits, so it's the same size square. In theory, not in reality, per my handwriting here. So that's S2. What is S2 pointing at? So it's pointing at the same thing. So S2, yes, is a copy of S1. But if we're trying to consider char stars to be conceptually bigger entities than just a number, but an entire string, clearly I've not copied the string because the same 4 bytes are being used for FOO\0. So now I claim I'm going to capitalize the copy here. So I do a little sanity check. If the length of S2 is greater than 0, like let me make sure that I have room for this string, what do? I take the 0th location of S2, and I change it to be the result of calling toUpper on the 0th character in S2. And I took that function from the string library that's up here. So you can see it documented. You can check out the man page. It's just a little function that does capitalization for me by remembering, oh, 65 on up is uppercase, 97 on up is lowercase, that whole deal. All right, but then I claim here comes the original, S1. Here comes the copy. But the problem was that both the original and the copy were the same. They were both capitalized. But pictorially, that should make sense. So how do I fix this problem fundamentally? If I want to maintain the original and then make a copy, the latter of which only is capitalized, what needs to happen on a high level? Yeah, so we need new memory, right? So we need to take 4 bytes that have FOO\0. We need another 4 bytes, and then we need to fill that array with that particular copy. So let's go ahead and open copy2. You have a printout of this as well. Let's scroll on down here. And now this is the new magic. And this is something that's going to become very useful, because thus far, pretty much any program you all have written, if it takes any form of input, the only way you've been able to get input from the user is by way of getString. But you'll see, and certainly you want, to write programs that take far more interesting input than just a string here or a string there. And you're not going to be able to use the getString function. You might want to get a new record in a database. You might want to read in an entire web page, maybe not in C, but in another language. You're going to need dynamism with which you can allocate as much memory as you want, but on demand. And the means by which you do this is this little guy here, malloc. So what am I doing in this version? The first few lines of code are identical. I declare a string called S1, and I get a string from the user. So that picture, again, looks a little something like this with a pointer to the first chunk of memory. Now, though, I do this. I call a function called malloc for memory allocation, and that takes a single argument here, the number of bytes you want allocated for your use. So I had to do a little bit of math. I could have just hard-coded 4 in here, but that's probably not the point of the exercise. So let me figure it out dynamically. How many bytes do I need? I need the length of the original string plus 1 times the size of the piece of data that I want to store in that location. So strlen of S1 gives me back an answer of what in this specific example from before? So 3. So 3 plus 1 times size of char. And the size of char, what does this return? So you're right. So this returns 1 byte here. So not 8 bits, 1 byte. Size of returns bytes. So that's 4 times 1. 4 bytes comes back. And just a little sanity check. Why this plus 1 here? So because you need the 0 character for the end of the string. OK, so let's see what happens next. OK, so int n gets string length of 1. OK, so this is kind of a boring for loop that iterates from 0 to n. Oh, this is just using array notation to make a copy of S1's ith character and put it in S2's ith character. And then finally, at the very end, I need to make sure to install a \0 here. Those following along quite carefully might realize that, is this last line really necessary? If I really wanted to be nitpicky, I could delete this, but what do I need to change to make sure I have a \0 at the end of the copied string, S2? Good. So I need to, I don't need to hard code in a \0. Let me just steal the one that's already in S1 and make a copy. Which way is better? It's not really clear. The only reason that I might want to do this for sure is just to ward off the possibility that S1 is somehow broken or corrupted. At least this way I know S2 is going to stop at one point. But for the most part, these two are equivalent. And now what do? Capitalizing copy. So why am I executing this line here? Why am I checking the string length of S2 in this context at the bottom of the program? Like, what is bad about not checking the string length of S2? What might I do blindly? Sorry? So I might try changing a null character to an uppercase character. Or really, if this string S2 has 0 length, I'm saying go to the first byte in S2. If there's nothing there, some of you have made this mistake. I mean, maybe we can do a little confessional, even with problem set 3. How many of you are willing to admit you have created a core dump in your directory? OK, so now those of you who weren't willing to put your hands up, now your hands can go up, right? So you're in good company. So it's a lot of you. And odds are those hands who didn't went up, I think it's more likely that you haven't started the P set yet, or that you're just not fessing up, since it happens to the best of us. And let's see if I can't induce this behavior myself. So this is my original program. So what do I want to do to maybe mess with my own program here? Well, let me do something like this. Let me go ahead and, let's say not up to n, but I kind of screw up. And I do something, whoops. So instead of making a copy from 0 up to n, let me be really obnoxious and try copying 100 bytes, only a few of which probably belong to me. So I'm going to make copy 2. I'm going to run copy 2. I'm going to type in FOO, which is a string length of 3. And OK, that seemed to work. So realize, too, these problems you're running into with memory are not always easily chased down. And this is, again, why GDB can be so powerful, because sometimes, because of the way memory is managed in a computer, sometimes you can touch memory that doesn't belong to you, but nothing bad happens. But sometimes it does. So with memory, can you actually get these sort of non-deterministic bugs, because things happen differently sometimes when you run a program if a user input is influencing the behavior. So let me try this again. Let me recompile, this time using 1,000 for copy 2. So what I'm doing now is I'm blindly copying 1,000 bytes from S1 into S2, even though I did not allocate that many bytes for the copy. Whoa. OK. So bad stuff just happened, right? So that's the takeaway. If I do an ls, there is my core file. If I do an ls-l, what you'll see is the long listing. So this is a lot of dates and times. But if I look for core here, notice that apparently this dumped out 442,368 bytes of memory. And if you really want to be more like a human, you can do ls-lh for human readable. So my core dump is apparently 432 kilobytes, which is apparently roughly how much memory that program was using at the moment I screwed up. So the computer dumped the contents of that memory to the local hard drive. So let me actually do something with this core dump. Another trick that we can introduce with GDB today is this. I can run GDB on copy 2, and then I can go ahead and type run. And then I can type foo, and now I get this mess. But you can also do sort of some forensics with GDB. If you already screwed up and you therefore have a core dump file in your directory, you can tell GDB to use that. You say GDB, name of the program, and the name of the core dump, which is typically core, hit enter. And what you'll see now is, let's see if it's actually, it's not terribly useful here. But it did tell me that this program, when the core file was generated, aborted with signal 6. And actually, You know, I would also email help@cs50.net if I got this error, because this is not actually that helpful. So what's actually going on? Well, let's take a quick look by running the program. GDB of copy2, enter. Let me go ahead and break in main. Let me go ahead and run. And now it's going to say something. Now I'm being prompted to say something. I'm going to type foo. Now it's doing a little sanity check. Now it's allocating the additional memory. And let me do something here first. I'm going to print S2. And look, there's just garbage there. If I then type next, let me now print S2. And now there's different garbage. Why is there different garbage all of a sudden? What's that? Well, so I haven't put anything in S1 yet. So S2 originally by default had some garbage value here. So now it seems to have some new garbage value. But that's actually to be expected, because what does malloc return? Quite simply, it returns the address of what? Just the address of a chunk of memory, however many bytes you asked for. But it makes no claims as to what's actually at that address. And so we just have different garbage because we've been handed a different address. All right, let's get to the point where I actually screw up. I check the string length. If I print n, n is indeed 3. Now here's my loop. So you know what? Let me go ahead and type next here. OK, that seems to be fine. Next here. Let me do a quick sanity check and print S2. And really, I'm just futzing around. But, oh, some progress. Now I at least have an F at the start of S2. Let me go ahead and type next again. Next again. Now let me print S2 again. OK, F-O-O. Oh, that's an accented O. So it looks coincidentally like garbage and not an accented O. So let's do it one more time. Next, next. Now let me print S2. Good. There's still some garbage. So let me do one more iteration here. And now print S2. Aha. Why does the string all of a sudden look perfect? Because there is a null 0. And one of the things GDB does for me is it realizes, oh, if I see character, 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 \0, let me just show the user the thing before the \0. Now, if I go ahead and type continue, I'll see that something bad happens here. There's mention of heap over here, which is an interesting keyword. Let me go over here. Oh, so this is interesting. glibc detected invalid pointer when I called free. So some really bad stuff seems to have happened, and apparently the result of messing with my own memory. So why is this then a good thing? Well, we now have the ability to do what we want with memory and pretty much anywhere we want, albeit with this downside. So the quick teaser here, at the bottom of this picture, finally, we're now putting back the top of this picture. At the bottom of this picture is the so-called stack. Quick review, what goes on the stack? What kind of stuff? So functions frames, which contain their local variables, and also functions parameters. And when we played around with recursion a couple lectures ago, and I just kind of foolishly or naively implemented a recursive program, a function that called itself, and I just let it call itself thousands of times, millions of times, it eventually segfaulted, which again hints at a memory error, because what happened to the stack? Well, it kept putting frame after frame after frame after frame on the stack, but clearly is your memory in reality limited finitely. And in fact, most operating systems, as we've said, somewhat arbitrarily say you cannot use more than 2 gigabytes per any given program, and that generally has to do with the size of the int or whatnot that they're using. So in that recursive program, bad things eventually happened when my stack overran this thing called the heap. Well, what is this heap? The heap pictorially is generally just drawn at the top, and this just means that the heap is where dynamically allocated memory is taken from. Anytime you call malloc, henceforth, it comes from that portion of memory called the heap. And as the arrow suggests, the more and more memory you allocate with malloc, the closer and closer and closer you get to the stack. So you get sort of these competing beasts, where one is where memory gets allocated by you via malloc, but if you start to push the limit with malloc, you too might end up crashing your program. Now, what about those things on top? Well, there's initialized data and uninitialized data. Well, those of you who've tackled problem set 3 already a little bit know that there's at least 2 global variables. What are those? So board and D for dimension. And in fact, if I go ahead and open this, so I'm going into CS50, pub, source, psets, pset3, 15, 15.c. If you've not seen this yet, not to worry, but thank you. Yeah, the laughter helps, yeah, embarrassed. Good lesson. So this is pset3's 15.c file. So this is one of the framework files that we give you for this problem set. And there's two global variables. One is called board, and it's a two-dimensional array. So as we said a while ago, you can have a two-dimensional array, and you just declare it by specifying the width or the height and the width. Doesn't matter which way you view your world, so long as you view it consistently throughout your program. And actually, just this morning, we were corresponding with one of your classmates who, very reasonably, not to poke fun at all, had some weird bug where every time he ran one of his functions, one or more of the elements of his board, one of the numbers from 1 to 15, was just changing inexplicably. It was becoming -1 or something weird. And so what the problem actually ended up being was he had in some line of code of his program, hope no one tries to copy the distribution code because we're now writing on top of it here, he had a line like this: for int I gets 0, I is less than dim max, I plus plus, and then he probably had a nested loop or something like this. I'm hypothesizing partly, j plus plus, but there was a silly mistake like this. And what was happening was when he was allocating, or let's see, board, j gets, let's say I, just arbitrarily. So there's a bug in this loop. What is the bug that I introduced intentionally? So I'm iterating not from I is 0 less than dim max, but rather less than or equal to. So I'm actually going too big here. But the interesting thing was, every time he did this, oh, that's what it was. It was his variable d that was changing. So d was somehow changing even though he was never touching the variable d. And yet if you look back now at the proximity of this area of memory called uninitialized data and uninitialized data, those global variables end up there. And if you give them a default value, they're put in the slice of memory called initialized data. If you declare, as we've done, two global variables without giving them default values, they end up in uninitialized data. But because I had written these things back to back in the file, GCC had laid them out in memory back to back, which means if with your loop you iterate ever so slightly too far, guess whose value does in fact get clobbered? D, because it was literally right next to board in memory. And this is the simple explanation. And then finally, the text segment up there, it's a weird name, but it's historically accurate. What is the text segment of your program? So those are actually the zeros and ones that compose your program on disk. When you compile a program into a.out or any executable and then run it at the prompt, well, the computer has to be able to read those bits back through its CPU, and it puts them at the very top of this chunk of memory. So there's an interesting danger now that arises with the fact that most stuff in memory is allocated one after the other. The stack, the fact that it does this, very nice and conceptually neat, but it's very dangerous because adversaries or malicious coders can actually exploit this. And so one of the most common ways of hacking into a system, even to this day, one of the most common ways of breaking into a website or some other piece of software is to feed a program more bytes than it's expecting. So as this student did accidentally, by stepping over the bounds of his array into a variable d, what people generally do, and sometimes it's by trial and error, is they try to input not just some normal text like foo, but they try to paste into a program essentially executable code, zeros and ones that they wrote, that if you can somehow slip them into a program's memory in the right place, those zeros and ones might actually get executed. So if you've ever had a friend who downloads a crack for some piece of software to circumvent the serial number or whatever, that's often the result of someone figuring out exactly where in code, and now everyone's attentive, where in code that if condition is, or where that variable is, and somehow trying to clobber its value or tell the computer, unbeknownst to it, to move to a different function altogether and not that particular one. Even to this day, there's so much software out there that's still written in C, C++, and similarly dangerous but powerful languages that maybe 50% of the time still are exploits the result of buffer overflow attacks. And in fact, when the iPhone had just come out a couple of years ago, some of you might be familiar with this idea of jailbreaking it and being able to put your own software on it, pull it off of AT&T's network and put it onto T-Mobile. And 2 years ago in 2007, we actually distributed in CS50 the crack code for the iPhone because someone had written it in C, posted it on the internet, and by running this C code on your iPhone, could you take advantage of a stupid mistake an Apple developer accidentally made that did not check the bounds of an array? And so this very clever or malicious person who wrote this code was able to take advantage of that and to insert into memory data that was not expected. Let's take a 5-minute break. All right, welcome back. So this was the article actually 2 years ago that I think I read like the morning of lecture, and it was this was posted on a popular website called Engadget. iPhone, iPod Touch, jailbreak code posted, and I went into our CS50 archives, and here is in fact that code. I'll link to it on the website. I mean, this was publicly available. We're not really doing anything nasty here. But what is perhaps the academic value of glancing at this is that although we'll just glance at the code, all of the code that this fellow wrote just boils down to some basic C constructs that we've been teasing apart over the past couple of weeks. So this is the code. Exploit for the iPod, iPhone by Takarta, Dre, and Niacin. Credit for the discovery goes to Tavis. All right, so we have some sharp includes up here. This is actually a C++ thing. So for those familiar or unfamiliar, C++ is kind of like a new and improved version of C, a superset, if you will, with additional features. They're definitely distinct, but they're very much related. Here we have a function. I mean, this stuff is all fairly familiar. We've got some parameters defined there, a for loop. Oh, and this is interesting. We'll actually glance at this briefly today. C allows you to declare something called a struct. So there will come a point very soon where it's insufficient to represent pieces of our program with just chars and ints and strings. You kind of want to represent a whole student object or a whole person object. You want to represent an entity that might have multiple components to it. And you can do that with this piece of syntax called a struct and define your own data structures. If I scroll down here, we see some more struct stuff. Where's main? Where's main? There it is. So there's the familiar main. So this fellow would not get very good points for style, right? I have yet to see a single comment in here, but maybe that's one of his points. We got some hexadecimal. Apparently that comes in useful, in handy when cracking iPhones. And then there's some fairly esoteric-looking stuff. But as I was talking with one of your classmates during break, what often is the workflow, and I don't know the specifics of this particular attack vector, is for people just to bang on programs or bang on websites. And by this I mean give them 1 billion characters and see what happens. Give them 0 characters and see what happens. Generally, bang on someone's code, which we encourage you to do to your own, because the teaching fellows will then do that themselves, because very often if you push hard enough, you start to find weak points in programs. And in fact, what adversaries generally thrive on is finding bugs in programs that cause them to crash, because even though you, the user, might actually get really annoyed when your program or when some website crashes as the result of some unintended behavior, that really makes an adversary drool, because generally, as we've even started to see here, when there are mistakes made, you can induce unintended behavior, and sometimes by injecting data that shouldn't actually be there. And so what happens often is trial and error. You bang on a website, bang on a program, voila, it crashes, it core dumps. Then the fun starts, at least in the eyes of these folks, because then can you finally start to think about why did it crash and how can I maybe take advantage of that. Now, in the case of iPhones and things like this, it really is a cat and mouse game, right? Because Apple quickly fixed whatever exploit, whatever bug this fellow took over, but it's a cat and mouse game in that this has been done several times since. So it's much, the adversaries, frankly, probably have the advantage in all of this because we, the good guys, have to fix every one of our mistakes to keep our code and our programs and our data safe. The bad guys just have to find one flaw or one mistake. So the tables are by nature fairly imbalanced. I thought I would show you this too. This was shared by a classmate. Now that you have a bit more comfort perhaps with crazy looking syntax, this is linked to on the courses lectures page, and it's kind of a witty, jokey thing that someone spent a lot of time on, coming up with different snippets of code that different personalities or people might write. So someone in high school or junior high back in the day might have written a program in a language called BASIC that, as I said, has explicit line numbers, looks a little simple like that. Then maybe in college it gets a little more sophisticated. After that, maybe in CS51 you start using a language called called Lisp or Scheme. Looks a little something like that. Then you start to become a professional, and the code starts to get longer. A lot of the examples just get a little crazy, but it speaks to this tendency to over-engineer a problem. This is written on a Windows platform, just a ridiculous amount of code. All of these programs implement Hello World. Then things start to come back down to neat reality, apprentice hacker. So the geeks in the room might actually like to play with some of these because you can run them on nice, most of these programs, if you know how to compile them or how to interpret them. But I think it gets funny sort of toward the bottom when it becomes a little Office-like or Office Space-like. So now we have the new manager printing something in BASIC, middle manager, if you're familiar with a little command like this, senior management, and then the chief executive I thought was the funniest. So fun with geeky humor. OK, so we promised to take the hood off of the CS50 library. And this is what you've been taking for granted all this time. But now we're in week 4 of the course. Even though some of the techniques you're about to see are a little more sophisticated than we'd expect, say, in current problem sets, you can at least now maybe take on faith that certain lines of code do what the comments say they do without getting perhaps a little overwhelmed by what just a couple weeks ago was entirely new stuff. So what I'm going to do is go back into today's source directory. You do have a printout of this. And this file, again, that we've been including via the preprocessor directive called sharp include looks a little like this. It's mostly comments up top. But then notice we are using a couple of values that are defined in these libraries here, float.h, limits.h. The Boolean data type, if you used it, we actually ripped that off from a standard library called standardbool.h. C did not originally come with a Boolean data type. People just used ints and used 0 and 1. But eventually people came up with a type def for that. We defined string in here. And then down here are just the prototypes or declarations for all of these various functions and the documentation for them. And as an aside, you won't have to do these sets of instructions at the top of this file. But just so you know, and can try to remember this 8 weeks hence, when you leave CS50, if you ever try to recompile your code on another Linux box or a PC or a Mac, odds are you may have some trouble with the compilation if you don't actually have copies of CS50.h and CS50.c. We've installed them sort of automatically on nice.fas in a way that just makes things work. So we included, just FYI, 8 months hence, directions up here, though a bit arcane, but they'll be a little more familiar in a few weeks' time, how you can continue using the CS50 library or in spirit any library like it down the road. Essentially, you have to create the equivalent of a .o file and then move it to a special place on your actual Mac, Windows, or Linux computer. So let's now look at the source code for CS50.c. So we copied and pasted a lot of the same documentation. Let's scroll down to getInt. Since that's perhaps one we've been using a lot, it's not many lines of code. So I stripped out the comments here, but let's see if we can't reason through what's going on. So while 1 induces what we would generally call an insert the blank, fill in the blank. Infinite loop, right? So infinite loops, often bad, not necessarily. Sometimes it is actually a very reasonable construct to code deliberately so that you can do something in perpetuity until something is true or false, at which point you can break out of that loop, as we actually do by returning from within. So there's different ways of doing this, but one approach is to embrace the infinite loop and just make sure logically that you will at some point break out of it, if that's the intention. So it turns out that getInt actually uses our own version of getString. So the first time Glenn and I sat down to write this code, we too started copying and pasting. And then we realized, wow, getInt is really similar to getFloat. And getFloat is really similar to getDouble. Maybe we should factor out these lines of code that we keep copying and pasting into every one of these functions. And so we did, and thus was born getString. So here we're leveraging a function we wrote elsewhere. And this factoring out of common code is perfectly consistent with the message we've been trying to send, that once your code starts getting a little longer, a little unwieldy, then can you start plucking out portions of it, just like we've done in the game of 15. The fact that you're handed a file with a whole bunch of functions, each one of which does something conceptually distinct, speaks to this idea of good design and modularity. So how are we leveraging this? We get a string up here. We call it a line, the variable called line. Then we do a little sanity check. If line is null, return int max. So here's where you trip over a little limitation or frustration of C. If something goes wrong in a function, that's supposed to return an int, how do you signify an error? Well, if you return 0, that suggests that you can never actually get the number 0 from the user. So let's pick something else. Maybe we return 123, 123, anytime there's an error. But the problem then is that the user can never type in the number 123 because you can't distinguish that from an error. So in short, you have to pick some value. Presumably, you're not going to pick one smack dab in the middle of the range, something like -1 or 0. Or as we've done, we picked the largest int possible. We decided, you know what, there's an upper bound on the number of ints that we can store with just 32 bits anyway. Let's steal one of those. Let's steal the very biggest of them, 2 to the 31 minus 1, and just say to the user, sorry, you cannot type in 2 billion, give or take. You can use anything smaller than that. So this constant, as suggested by the capitalization of it, is actually defined in one of these header files in CS50.h. So in float.h and limits.h, they're just some constants that someone else already defined for us that represent the largest possible int that you can represent with a C program. So we said, you know what, let's just return that value. So you, all this time, anytime you all have been calling getInt and just using its value, you know, you've never actually been doing the right thing, which is check and make sure it's a legitimate value. Technically, anytime you've been calling getInt, just like we've been calling getString and checking for null, you really should have been checking for int max. But frankly, in the first weeks of the course, really gets a little distracting, I think, if you're constantly checking and getting. So we ignore those details. But now in the documentation, you can see if line can't be read. If any error actually happens, it returns int max. And so this is, again, one of those RTFM moments. You just have to know what the possible return values are so you can handle any errors accordingly. All right, so let's assume there's no errors, because frankly, this happens very, very rarely in most contexts. So what do we do next? Well, this is a new function, sScanf, string scanf. So this function takes a string as input and scans it for special characters. And we're using this function to figure out, did the user type an int? Did they type a word, a char? We need to use some format codes. And just like printf uses format codes, so does scanf use format codes like this. So this is a little trick, and we won't spend too much time on the details of this, but just so you have a taste of how what this library's been doing and how it's been saving you trouble, notice, or giving you trouble perhaps, scanf is going to scan the line that the user typed in, and it's going to look for this pattern. It's going to look for a space, and actually because the documentation of scanf says this, one space or multiple spaces. The fact that I've intentionally included a space right there means allow any white space. The user can hit spacebar as many times as he or she wants, then look for an integer, then look for a space, one or more spaces, then look for a character. And this is actually kind of a clever trick that we did here. So these two variables here is a clever trick that lets scanf essentially return two values. So remember, a C function can't return two values. It can only return one. You can only have one thing on the left-hand side of the equal sign, the assignment operator. But we've had, as of Monday, this goal, this desire to actually change multiple values at once, I and j, a and b, x and y. So what am I doing with n and c that are just primitives, ints and chars? What am I doing with this ampersand? What am I really passing into scanf? Yeah, pointer. So the address of n, the address of c, which means now that I've handed him this roadmap to those variables, scanf can put anything he wants in those variables, which means he effectively can return two values, but that's an abuse of the terminology. He can alter or modify or mutate two values, and that's the goal here. And now finally, I know from the documentation that scanf returns the total number of variables that were read into. So I've handed it to n and c, but scanf doesn't have to fill those variables, because frankly, if the user just hits enter or a lot of spaces and no ints and no chars, I mean, he has nothing to put in n or c. So scanf returns the number of variables that were actually filled with values. So why am I doing this? Like, why the %c? Clearly, I want just one of those to be filled, right? Because I'm checking here for equaling 1. I only want one variable filled, the first one, n. What does it mean if the return value is 2, do you think? So there's a character, right? Just logically, if the return value of scanf is 2, not 1, that means both n and c were filled with values. But what does that mean? Well, according to the format codes, the number would have been put first because of the %d and because of the n. So if the user types something else, this something else, the first character of it, would at least end up in C. And so what this means is that if the user's trying to mess with me by typing something like 4, and then again my random string of the year, monkey, it's going to detect 4 and then m, but that's an error, right? Because we only want the number 4. So if the return value of scanf is anything but 1, that means the user typed in, yes, an int, but then some garbage. Or the user typed nothing, in which case the return value is 0, in which case it's also an error. So what do we do in the case of an error? We free the line. So we free the memory that we just got by way of getString. And then we tell the user to retry. So anytime you've seen in your own programs retry colon, it's simply because we hard-coded it into this function here. But if scanf does in fact return 1, what do? Well, we don't need the line of text. I don't need everything else the user typed. I don't need any spaces or whatnot. I just need n, so I go ahead and return n. And now a quick distinction, to be clear. getString allocates memory dynamically. With regard to our little picture from before, where does getString take memory from? So the heap, right? So getString, or in turn malloc, takes all of its memory from this area called the heap. By contrast, where do n and c live in memory? So they live in the stack. And we knew that from a week or so ago. Any local variables live on the stack. But the problem with the stack is that as soon as a function returns, as soon as getInt returns, the stuff on the stack goes away, it gets obliterated. It's no longer safely there. And this is why the heap is so useful and so neat. Because on the heap, memory stays where it is, and it doesn't get automatically overwritten as it does in the stack. Now granted, if you try to use too much memory, it will accidentally get overwritten, but not automatically. It's the stack that's whose memory is reused constantly as soon as the function returns. Which is to say, do I need to ever free a local variable like n or c? So no, it would be an error to free anything on the stack. You only call the free function on something that's been allocated on the heap, and that's why I only free the line, and I only free the line here. Well, let's now tease apart getString, since that's apparently what's making all of this possible in the first place. So getString is a little longer. We won't dwell on all of the details, but just to hint at the flexibility here. So getString first declares a string called buffer, but it initializes it to null. And that's just good practice. You will find that even if you don't need to use a variable yet, you will save yourself a lot of time over the course of your lifetime by initializing intentionally variables to values so that you know they are in fact something. Then I have some capacity local variable, an n local variable, and a character. Now this looks like bad style, but it's just because I've ripped out all of the comments from today's code. And it looks like there's this function. There is a function in C called fgetC, file getCharacter. Standard in refers to your keyboard. So what this is a loop that says keep reading character after character from the keyboard, store it on each iteration in a local variable called C, and then, and this is our clever one-liner, make sure that C does not equal the new line and does not equal this special EOF, end of file character, that happens if the user hits, say, Control D on most computers. Now this line of code here, which is best explained by the comments, does a really neat thing. If the total number of characters in the string at the moment plus 1 puts us over the capacity of the string, in other words, we have this variable called buffer. It's just a bunch of bytes. Currently, there are no bytes there because I didn't initialize it to anything. If the next byte would overflow this so-called buffer of memory, just intuitively, what had we best do if we want to be able to grow dynamically? The buffer is this big. The user just types something in. I need to go guess for more memory. Now let's fast forward a few moments in the story. Suppose that I now have 10 characters, but the user types in an 11th. Problem is, I can't just overwrite the 11th space because I'm going to overwrite the \0. So what getString ultimately does is it starts with a buffer like this. The more and more characters it finds at the prompt by way of this fgetC function, it decides, oh, you know what, let me double the buffer size. Then let me double it again, and then double it again, and then double it again. So it's literally growing dynamically. It's using a function called realloc, which has the effect of reallocating memory if it's possible. You hand it a pointer, say, I don't want this memory anymore, I want more, give it back to me. So that's what this ultimately does. And then finally, at the end of this function, we are sort of a good neighbor. So we then decide, you know what, if I've just been doubling and doubling and doubling this buffer, but now I actually didn't need all of that memory. I just needed an extra 1 or 2 bytes, not all of the memory over here. These 3 lines of code here, as you'll see in your printouts if you reason through it, simply allocates just enough memory using alloc, using n+1 for the new line character. We use a function called string ncopy, stir ncopy, which copies one to the other. And then we free this excessively large buffer so that what we hand you, the student, the user, is only as many bytes as you actually need. And so this little exercise today of finally peeling back the layer and looking underneath the hood is precisely in the spirit of taking these training wheels off. And next week, we dive in to get more powerful techniques still. We'll see you on Monday.